This is RTP. This is RTP180.
All right, thanks everybody. Thanks for coming. I really like to look at a big picture of my face to get excited. All right, so let's get this going. All right, so I want to talk today about our dark universe and what's really exciting today in cosmology. I want to start with a movie, and this is kind of how I think that we all think about space. We have all seen these pretty pictures that NASA's released and other telescopes have released. So what you're going to see here is basically a large portion of the sky, and then some NASA scientists decide to just stare at one small part of the sky and just stare at it for a really long time. So what you're going to see is basically, oh, that lost. That's not what NASA saw. Okay, great. All right, yeah, we're getting there. That was my joke almost. All right, so NASA is staring on part of the sky. So basically, you saw the constellations, and this is basically just some teeny part of the sky where nothing was expected, and now nothing's there again. Okay. How are we doing? All right. This is our dark universe.
This is why we can't have night.
Yeah. It does feel fitting that, yeah, I am talking about a dark universe, and all I get is darkness. So, oh, great. Okay, let's try this again. Oh, nope. All right, so maybe we're going to zoom in. Hold on. Nope. All right. So, okay, so basically here, videos are not working. But oh, man. Okay. This is why it's hard to go first. Great. All right, any questions so far? Great. Okay. Press the side button. Yeah. No. Okay, I'll keep going. Okay, basically what you would have seen if this zoomed in is in the smallest part of space, there's just billions of galaxies, billions of stars in those galaxies. So we kind of have this idea now of space that wherever you look, there's just lots of stuff, right? That's kind of how we think about it, that no matter where you look, how far back in time you look, there's lots of stuff. Now, in reality, this is the pie chart of our universe, where kind of everything that you learn about in science class as a kid, these are made of atoms. This is kind of the normal stuff. This is what makes you and me and the galaxies and stars and planets. That's 4% of the universe. Then the rest of the universe is something called dark matter, and that's about 26% of the universe. And then there's another thing called dark energy, and that's 70% of the universe. Now, dark energy is repulsive, dark matter is attractive, and that's about all we know about either of them. Light does not interact with either of them, and they're complete mysteries to us. So, kind of as you saw before, basically, astrophysicists understand 4% of the universe, and really, the rest of the universe is just totally dark. So that picture of the dark screen is a good picture of the universe. And this actually is what the universe looks like, realistically. Right? That's pretty good. Now, what's amazing about being a cosmologist today is that it's really the only field in all of science where you could stand in front of other people and say, we understand 4% of what's going on, and you still think that we're kind of smart. And there's no other, there's just no other field that could do this. A kid can't come home with a 4% and his parents are proud of him. That's impossible. Now, cosmologists and kind of the astronomy community generally has felt okay with this model of the universe, basically this what we call a standard model, where 96% of the universe, we just don't know what that is. But lately we found a problem, and I'm right in the middle of this problem. And the best way to explain it is with a doctor's growth chart. So you probably all remember either taking a kid or going yourself to the doctor, and you get measured, when your height gets measured, and the doctor says, okay, well, you're this tall now, and when you grow up, you're going to be 5 foot whatever. We basically can do the same thing with the universe, and this is kind of what we call our end-to-end test of cosmology. Basically, we have a picture of the universe as a baby. This is a picture of the universe from the cosmic microwave background. And we have a picture of the universe today. This is what I work on, basically the universe as an adult. And what you'd expect, if our standard model of cosmology is correct, is that our doctor's curve should connect basically the size of the universe as a baby to the size of the universe as an adult. So it forms a prediction, and we can actually check that prediction. Now, the problem is that it doesn't work. Basically, the difference is like if from the baby picture, the doctor predicted that you'd be 5'7", give or take an inch, and you turn out to be about 6'1", give or take an inch and a half. This turns out to be the biggest tension in all of cosmology. Basically, there's 3 possibilities of what could be happening. One is that we've somehow messed up our baby picture. One is that we've somehow messed up our picture of the universe today. And the other, the really exciting one, is that maybe that standard model of the universe, this picture of having dark energy and dark matter, and we don't know what that is, maybe that's incorrect. Now, just to kind of give you an idea of why we should be confident in kind of how we do the measurements of the universe today, because this is what I work on, basically it's this 3-step process. And what we rely on is something called standard candles, where basically if I told you that all the lights in this room were made from the same factory and had the same wattage and were exactly the same, then if you saw a light that's further away, that looked fainter than another light, you could say it's this much further away than that other light. So basically we're using standard candles, and to calibrate those standard candles, we need something a geometric calibration. We do something called parallax. So if I could have you all do this with me, basically if you could put your hand over your eye and reach your thumb out, and all you have to do is move, look at your thumb relative to the background, and just put your other hand on going between both of your eyes. And what you should see is that your thumb looks like it's moving, even if your thumb isn't moving. So if you want to figure out how far your thumb is away from your face, all you actually need to know is the distance between your eyes and measuring that angle. We actually use that same technique in kind of our first step of what we call the distance ladder, and that calibrates our standard candles. Once we do that, we can make a very accurate measurement of the universe today, and that measurement of the universe today is in tension with the measurement of the universe as a baby using our standard model. Okay, so what could be the problem? I'll just say it very quickly. Well, we don't understand 96% of the universe. A lot could be the problem. That seems pretty reasonable. Now, for dark energy, this is kind of where it seems like the problem should be. What we think dark energy is the energy of a vacuum, the energy of nothingness, where in nothingness you have particles and antiparticles, and there's popping up and popping back out of existence. And we have a theory that should be able to predict what the energy of that vacuum should be, but then when we measure how much dark energy there is, it comes nowhere close to what our theory predicts it should be. So that's a good sign that something's going wrong there, but we don't know what that is. Okay, so what's going to happen? Well, basically, the whole astronomy community is dedicating huge resources, building these really big telescopes, and kind of I work on these samples of supernovae, these exploding stars, and to date, we've found about 1,000 of them that we could use in our analyses. And in 5 years, we'll find about 1,000 supernovae every 3 days. So we've hit 1,000, for all of humanity, and then every 3 days we'll just duplicate that sample. And what you hear about next is what's called kilonovae, and which could also be used to do this kind of measurement. And we've found one to date, and in 5 years, we'll find one about every month. So we're just going to be finding lots and lots of these objects that we could use to measure the universe. And the question is, what's going to happen with this tension? So I'll leave it there. Thank you very much.